Okay, AP students, this will be big idea 4 for our AP Chem review. We're going to do chemical reactions. I'm going to go through this a little quickly. Most of this we've done, well, a lot of this we've done fairly recently, especially the last types of reactions, oxidation, reduction, some of the titration stuff. So, but let's go ahead and get started. So, processes in chemistry, let's get this out of the way. Processes in chemistry can be physical or chemical. So the physical changes, physical changes are going to be phase changes or separations of mixture. This is not to be confused with like physical properties and chemical properties. So, but physical changes are going to be those phase changes. You're changing ice to liquid water. You're changing liquid water to steam. Perhaps a separation of two mixtures. If you had oil and water, you could separate them using a SEP funnel, and you would still have those two things apart. Chemical changes are going to be a little bit different. Generally, physical changes are reversible and chemical changes are reversible. You know, if you cut the grass, you can't put the grass back together, but it's still grass. That's a physical change, even though you can kind of can't put it back together. But usually a determining factor is figuring out whether or not you can change it back. For chemical reactions, they may produce energy. They may produce gases. They could also produce precipitates, or you could see color change. So that's evidence that they give off heat or light. So this produced energy could be heat or light. Yeah. Gases, precipitates, or color changes. Now, color changes is not always evidence that a chemical reaction took place. In fact, there's lots of physical changes that result in color changes as well. And so that's not necessarily evidence that a chemical change has taken place, but it can be. Dissolving actually has always been taught as a physical process. So if you put sodium chloride in water, it dissolves, but there are actually breaking of ionic bonds in the case of something like NaCl. And then you would separate it into Na plus and Cl minus. And while it's not really a chemical reaction, I mean, if you boiled off the water, you would get the sodium and the chloride back as the actual lattice work of the NaCl. But it is actually kind of ionic. Most of it, though, is interactions with the droplets or the dipoles in the water, which is physical, but not always. And so you can have something also called an induced dipole, which is kind of a weird thing we haven't talked a lot about. But if you had a magnesium ion, it would be attracted to the oxygen side atom of the water molecule, like so, dissolving the magnesium ion in there. But the magnesium ion might actually cause a dipole moment or pull the electrons that are in that molecule closer to it, causing what we call an induced dipole. So that's something to kind of think about. There are things called induced dipoles, which are generally caused by this highly charged molecule with something with a lot of electrons. Anyway, so chemical processes can be represented, of course, by chemical reactions. So if we have an example here, two different ones, but kind of the same, a complete molecular equation where you added potassium iodide. Now it says potassium iodide. It may tell you that it's aqueous, it may not, but it is aqueous in this case. Lead 2 nitrate, which would be PbNO3 2. It says plum bus nitrate, so that's the Pb2 plus and the NO3 minus. And if we get our products here, we get PbI2. Oh, I should have written that this was aqueous. They may tell you that in the problem. PbI2 would be a precipitate, and the other product would be potassium nitrate, which would, of course, be aqueous. Determining the aqueous and the precipitates is going to be use of your solubility song. Unlikely you're going to have to do a whole lot of prediction of those products, but you should be able to write a double replacement reactions. I would include the state signs if at all possible, especially solid, liquid, and gas. But I don't think that AP is going to, or College Board's not going to grade you based on those unless they give them to you in the problem. If they tell you what they are, they want you to write them. If they don't tell you what they are, it's probably okay. The net ionic equation, you would remove all the spectator ions like nitrate and the group 1 cations. So the nitrate, of course, and the potassium ions are going to be subtracted from there. So you'll end up with just your lead ion and your 2 iodide ions to produce the PbI2 labeled as that precipitate. Could label the ions in aqueous solution, that would be fine too. But at a minimum, make sure you're doing your state signs for your solid, liquid, gas. as those are the driving force for the reaction. Should say that most are going to want you to write the net ionic equation. That's what you're going to see most often. You could see them wanting to write a molecular equation, but most AP questions are always written in net ionic form. So in particular representations, if we were actually putting these things together, it kind of matters how many of them you have. So if they say things like equimolar, or they say something like equal volumes or equivolume for each of these solutions, then you'll have to make sure that you have the right amount of them. So for instance, that they said, oh, hey, I've got one beaker with the potassium iodide in it. So I would have some potassium ions and some iodide ions, right? Well, let's just say that they said you had 2 molar and 2 liters of it, right? That would mean that you had 2 moles of the Ki. And so you would probably need to draw whatever the appropriate number of those things are. Now, let's say they're adding it to the solution, I think was lead 2 nitrate, the other solution, blah, 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 blah. And they say, oh, well, you've got equivolume and equimolar. So we're saying it's the same. This is also 2 molar and 2 liters. And in this case, we would have 2 moles of the PbNO3, 2, yeah, lead 2 nitrate. So in that case, I would draw my 2 moles of the Pb2 plus, kind of somewhere in there, and I would draw the nitrates, but I'd have to have more nitrates, right? Because there's 2 of them for each one. So I would draw a total of 4 nitrates in here. And then what's going to happen as a result, they're going to get together. And then this, of course, would be a larger volume, twice the volume, right? It would be 4 liters total. And then you would probably have to figure out what your ion concentration is remaining in there, and perhaps how many moles of lead 2 iodide you produced. So one of the solid, I'm just going to write it on the bottom, would be the PbI2. Solid would be like a pile of solid there on the bottom. And if you did this, you have 2 moles of iodide ions for every 2 moles of the lead ions. Let's see if I'm doing this correctly. I'm looking at my drawings here. So if I did that, I would probably extinguish all of the iodide ions, since I have 2 moles of them. And I have 2 moles of the lead ions, but I'm only using half of them. So I'd have some Pb2 plus left over. I also am going to have all of my nitrates left over, because those are going to stay ionized as spectators in solution. Just draw 4 of those bad guys in there. And then, of course, I'm going to have the 2 moles of the potassium ions. They're also spectators hanging out in solution. So what I would what you would end up with at the end kind of matters. You've changed the volume here. You've got double the volume. So you don't have 2 molar potassium ions. You've got 1 molar potassium ions. And you've got full 2 molar and your KNO3 ion, your KNO3, look at me, just your nitrates, sorry, my mistake, of the nitrate ions. The 2 molar of the nitrate ions. And let's see, what else have we got here? Would we have 2 molar? No, I think we'd have 1 molar because we have half the volume. Let's make my smaller here. And we'd actually have, oops, that's not the eraser. We'd actually have 1 molar. 1 molar nitrate, wouldn't we? 2. No, it's 2. Sorry, there are 2 nitrates for that. My bad. It would be 2 molar nitrate ions. That's correct. Because it was 2 molar lead 2 nitrates. So I had 4 moles of nitrate ions. So 2 molar nitrate ions and 1.4 liters total. My Pb2 plus would have a concentration of actually 0.25 molar. And so you're going to have to kind of figure this out as far as how much of them you're actually going to use. That can't be right. Is it 0.25? I'd have 1 molar left over. It'd be 0.5 molar. I used up 1 mole of there, and then I've got 2. It would be 1 molar. Lead ions. Yeah. The same as whatever the potassium was, would be what was left over with the lead. Yep, that's correct. So you would have to draw these. So if you're asking for what the limiting reagent is here, the limiting reagent would actually be your I minus. Yeah, that concentration of the I minus is going to be limiting what I have here. So be able to draw these. I know it's been a while since we've drawn a lot. You'll have to draw or at least identify some drawings in on your exam for sure. So if we go down here, balanced equations actually allow for a mole ratio to be used in stoichiometry. Use of molarity as a conversion factor is important, especially for acid-base reactions. So your molarity is going to be the number of moles over liters. So you use that as a conversion factor to convert to liters or to convert to moles, depending on what you're looking for there. Usually it's going to be moles you'll need for a mole ratio. And then if you have any stoichiometry with gases before you do it, make sure you use PV equals nRT to find the number of moles before you carry on with the rest of the equation. Let's see, should we go over to titration? We'll go ahead. Well, let's go do the titration. So titration is actually used to analyze a system where you don't know the concentration of one of them, but you do know the concentration of the other. Usually the titrant and your known concentration is at the beginning, most of the time. So usually your known is going up here in your burette, and your unknown is the thing you're analyzing, your analyte. So this is usually your unknown. It's not always that way. It can be reversed. You can certainly do stoichiometry, or you could do Navier-Nabvub. Navier-Nabvub's a little bit easier. Do not write M1V1, M2V2. It is not a dilution. You're adding two things together, actually. So let's say we did, let's do an example of this. And I'm going to take this known unknown away here. But let's say our example is that I'm going to take 25.0 milliliters of magnesium hydroxide, and I'm going to titrate it with hydrochloric acid. Okay. And let's see. Let's say that it took, in the final reading here, would be 36.02 milliliters of the HCl that's added. Yeah. And so down here, I have my magnesium hydroxide initially. And my initial reading up here was, let's say my initial reading, let's say, was 1.00 milliliters. That's kind of convenient. And then what's going inside here, our titrant will actually be our HCl. And let's say it's 0.15 molar HCl. So probably would have been better to write this as a question, but whatever. So we've got 0.15 molar HCl. We can subtract the two, the initial and finals, to figure out how much we added. And then we could use stoichiometry to find out how many moles of the magnesium hydroxide and then divide by the 25 milliliters. A couple different ways to do that. It kind of depends on you, or you could Navier-Nabvub it if you wanted, but this way works well. Let's go ahead and do this. So I'm going to write my balanced equation first. So if I've got magnesium hydroxide and I'm adding to it hydrochloric acid, I need to get some space to balance this bad guy, plus the HCl, I'm actually going to get magnesium chloride, and I'm going to get some water. To balance this, I'll need a 2 in front of this and a 2 in front of this, and I've got my reaction. If I were going to do this stoichiometrically, I would start with the volume that of my known, which is 35.02 milliliters of HCl, and then I'm going to multiply that by the molarity to get my moles, and then do my mole to mole ratio. To do that, I'm going to actually need to change these milliliters to liters. This is liters of HCl. At that point, I could then use my concentration, which I say is 0.15 moles of HCl per 1 liter of HCl. And then I could do my mole to mole ratio. There are 2 moles for my balanced equation of HCl for every two, listen to me, for every 1 mole of the, excuse me, of the magnesium hydroxide, GOH2. And, oh, that's kind of it right there. Oops, let me fix that real quick. So actually that's kind of the stoichiometry right there. At that point, I'll have the number of moles of magnesium hydroxide. I got 2.6 times 10 to the negative 3 moles of the magnesium hydroxide. I would then need to divide this by the number of milliliters, which in this case, or liters actually, is 0.0250 liters, to find what my answer is. What I end up getting here is that it was 0.11 molar magnesium hydroxide. Now, if that's what I was asked to find, was what is that unknown concentration, I'm kind of finished there. That's it. They could ask subsequent questions like what is the final pH of the solution or whatever, but we'll deal with that when we talk about acid-base reactions in buffers. But anyway, another way to do this would use Nevenub, which may be a little bit easier. Why did I write a plus sign? Nevenub. And so my normality of my acid was 0.15 normal. Now, the reason I say that is because the acid only has one hydrogen. The volume of the acid, I think, was added was 35.02 milliliters. Don't have to do a conversion to liters. The normality of the base is what I'm going to solve for, and the volume of the base initially was 25.0 mils. So I could go solve for my X here, which is actually my normality, which would be 0.21 normal. And so if I divide that by 2 to change to molarity, I end up getting that it's about 0.11. If you look at your sig fig stuff, you actually did your division, 0.11 molar MgOH2. Two different ways to kind of do the same problem. I think Nevenub's a little bit easier. Just please, please, please do not write M1V1 and 2V2. That will be counted entirely wrong. So if I scroll back up here, I'll go over the traditional reactions and explain them. I'll come right back and do that. So types of chemical reactions. So in AP, there are actually only 3, even though we recognize the 5 types from advanced chem. So advanced chem, I think we had, let's see, we had addition, decomposition. I was going to say synthesis, but that's already addition, decomposition, double replacement, single replacement, and combustion. Here in AP, they've kind of grouped them together. So redox reactions will also encompass combustion reactions and some addition and decomposition reactions. Acid-base neutralization reactions, they label alone, even though most of those are double replacement. So, you know, you're not wrong to call them double replacement, single replacement, synthesis, whatever. But AP kind of groups them into certain categories, and these are the 3. So the first one is that acid-base neutralization. So this is where you transfer a hydrogen, you actually produce water as a product. So, you know, and then there's different definitions of what these are, but the one that we use most frequently is Bronsted-Lowry. So you have an acid and a base that'll get together to produce the conjugate acid and the conjugate base. The conjugate acid from the base, and of course the conjugate base from its acid by losing or gaining a proton. So in the case of this next example here, HF plus OH minus yields H2O and F minus. The acid would be here as HF. The conjugate base would be the F minus. In this case, the base would be the OH minus, and the conjugate acid would in fact actually be the water. So just kind of showing you just one of those examples. They may ask you to write, for instance, a conjugate base of a certain acid, and you just take off one of the hydrogens or multiple hydrogens, but usually it's only a single hydrogen that you remove before that happens. Compounds that can act as both an acid and a base are actually called amphoteric. Another term used sometimes is amphiprotic. I wouldn't use that, but amphoteric is a substance for something that can act as an acid or act as a base. So if I were to look at HCO3 minus, HCO3 minus, when it reacts with water, can actually produce carbonic acid and hydroxide ions, which is what it typically does. But there is the idea that perhaps it could form hydronium ions as well. So HCO3 minus might connect with water to produce, you know, CO2 and H2O as a result. Highly unlikely that that's going to be the case. Oh, sorry, H3O plus. What am I doing? H3O plus. Oh, no, that would be CO3 2 minus. Well, what am I doing? CO3 2 minus. But it's highly unlikely that's going to occur. It acts more predominantly as a base, but in certain circumstances, it could be forced to kind of lose that hydrogen. But amphoteric substances are those that can gain or release hydrogen ions. They can act as an acid or a base in solution. So redox reactions, there's actually going to be a transfer of the transfer of electrons from what is oxidized to what gains the electrons, which is what is reduced. So you'll have something that's oxidized and something is reduced. You guys probably, of course, remember your oil rig, right? Oxidation is loss and reduction is gain of electrons. We're going to use half reactions to balance these. That is the best method, I think, to balance equations in terms of redox. They can be balanced using an oxidation state method, which is shorter, but it doesn't encompass the acidity and basicity of the solution. So the half reaction method is, of course, far better. So here's an example here. And let's change this dichromate here to instead oxalate. It works better with the dichromate than the oxalate anyway. So it says potassium permanganate reacted with sodium oxalate in acidified solution. They probably are going to go ahead and tell you that the products are going to be manganese ion and carbon dioxide. That would have been helpful. I'm going to write it as though we knew what they were because they don't ask you to predict them anymore. But MnO4 minus would be the potassium permanganate taking off the group 1 spectator. And the product here would be Mn2 plus. They would likely tell you that. They will tell you that. And then oxalate is C2O42 minus, and it is going to produce CO2. So we would go through and balancing it using the same half reaction method that we've used recently, actually. So here I've got one manganese on both sides, so both my manganese ions. I've got some oxygens on the reactant side of the permanganate half reaction. So I'm going to need to add 4 waters here. And then to balance that, I'm going to go ahead and add 8 hydrogen ions. Now I need to look at the charge, which is, well, actually, yeah, I've got all the elements balanced. I need to look at the charge. The total charge on this side is +7. So the 8 plus, H plus, and then that 1 from the permanganate. And over here is +2. So I'm going to need to add 5 electrons to this to drag the charge down so that it's +2 on both sides. Rid of this +7 and +2. And then down there on the bottom for the oxalate, I've got a single carbon atom, so I'm going to need to balance that with a 2. And then that takes care of my O's and my carbons. So I'm just merely looking at the charge. And the reactant side is 2 minus and the product is 0, so I'll add 2 electrons here. I will have to multiply this one by a 5 and this one multiply by a 2, so I'll have the same number of total electrons transfer, which would be 10 here. And then if I add these together, I end up getting 16H plus 2 of the MnO4 minus plus 5 of the oxalate anions. Where's my yield symbol here? I think I've left off a yield symbol here. That's silly. Yields. The Mn2 plus. Oh, where am I here? I've lost my train of thought. 2 of the Mn2 plus, plus 8 of the H2O, plus 4 CO2. Yeah, there we go. That's better. And so that would be your final equation. You could box it in. It does say it's an acidified solution, so we would be finished. Had it been in basic solution, you would add the number of hydroxides to the hydrogen side and then even it out by canceling out waters as they're produced. For the last one in precipitation reactions, these are essentially double replacement reactions. You're looking for something producing mostly a precipitate, yeah. And it's going to be something that has limited solubility. So it could be liquid or gas that's produced as well. So in this case, what I'm doing is I'm combining hydrochloric acid and sodium carbonate. My products here, when I do this, are going to be H2CO3, which is carbonic acid, and sodium chloride. And so if I go ahead and write, I balance this guy out. I need a 2 here for my sodiums. I need a 2 here for my hydrochloric acid. H2CO3, you should know, is not going to produce H2CO3, but instead will produce water and CO2. And so that one is now written correctly. I could write this as a net ionic equation by ionizing everything and then crossing out on both sides. My end result would be 2 hydrogen ions plus my solid sodium carbonate, which I should probably label, is going to yield the H2O, which would be a liquid, the CO2, which would be a gas, and then the leftover ions on that side would be 2 sodium ions, as the chloride ions would cancel from both sides. And this would be your net ionic equation for this double replacement or precipitation reaction. So that's it for big idea 4 for chemical reactions. There's quite a bit to it. But the reaction prediction part of it is not something that you're going to see on the exam. They may have one where you're going to kind of look for a precipitate, one equation, but it's not going to be any more than that. The days of us having 15 reactions to predict imbalances is not really a thing. So that concludes this one. I'll see you guys for Big Idea 5, where we talk about kinetics. There you go.